All right, here we go.
Hello. Part two.
Part two, here we are. I'm so excited for this.
Yes, for anyone who doesn't know, we are talking about divisibility patterns and math and Darren's really cool research that he's doing. And
Thank
I'm
you.
here to listen and follow along because I'm curious. And yeah, I mean, I'm here to learn something. Hopefully, you learn something too.
Fantastic. And thanks for having me back, Janet. I really liked what we talked about last time. I got a slightly different approach I would love to take this time, but excited to
Awesome.
keep going with what we had been talking about.
Yes, yes. And I love your orange wall. You were talking about
Yeah.
how you're back in your childhood house, childhood
That's
room.
right. Yeah, because as you know, Janet, my partner and I, we live nomadically. We travel all over. So the last video, we were in Washington State. We've actually since driven all the way back to Metro Detroit. We're visiting family. This is where we both grew up. And so, yes, this is my childhood bedroom that when I was in middle school, I had the option to paint it however I wanted. And at the time, I was obsessed with Rubik's Cubes. And so I'll show you two of the walls. There's the orange wall over there, and there's the blue wall over there. And so, as a sort of challenge question to anyone's interested, if the ceiling is white, what does that make the other two colors of the
Ooh.
walls? If anyone can tell us in the comments, or I don't know if you are you into Rubik's cubes at all, Janet?
Mystery question. Am I into Rubik's cubes? I once tried to learn how to solve them, and it
Yeah,
was okay. But you know what? I recently read an article that
yeah,
was saying about how people are solving Rubik's cubes faster and faster as like the years go on, and that like
yeah.
that's an interesting development. It's like just
It
as much math.
it's nuts the level to which people can see like the pattern to undo. Because I have a method that I
Mm.
follow, so it's just like step by step. But people can
Mm.
just see the shortest number of moves and it's like, yeah, it's
Yeah.
mind blowing the amount
Yeah.
of how much that record has dropped over the last few years.
Yeah, yeah, I did
Yeah.
see. I will say the article that I saw was slightly towards the conspiracy theory side of like,
Oh yeah.
oh, and then people are going to be able to solve it in negative time, and then people are going to be able to time travel using
Yeah.
solving the Rubik's Cube in negative time. And then, like, oh, all the Rubik's Cubes from the past are going to take them that people have stopped using and bring them to the future and resell them so they'll like have 100%.
That's
So
hilarious.
it was an interesting read at the minimum.
I love that. Yeah, definitely. Time travel unlocked through Rubik's Cubes.
I love it. Great science fiction book right there.
Fantastic. Yeah, that would be a good one.
Yeah, I mean maybe we can time travel through your divisibility pattern
Right?
somehow.
Maybe we find some sort of topological equivalence to it all and then bend space time or whatever it is.
Yeah.
And yeah, there
Space-time
you go.
continuum. There you go.
It's funny when I was in an undergrad, I used to joke that I would go on and do a PhD in topology and then use that to figure out how to time travel. But I haven't accomplished that yet, but there's still time, I suppose.
I'm sure there is. And if future you figures it out, then they can tell you.
Yeah, right.
Oh, that would be fun. Maybe
Yeah.
not. I don't know.
Yeah, I'd be curious to see how time travel would. I feel like we're already living in crazy, crazy times to begin with. I'm sure time travel would just make it that much more crazy.
Yep, yep.
Yeah,
There is a mess, there is a magic in the mess, and a fun if we don't mess it up too much.
exactly. Exactly right. Well, what do you think? So last time we talked a
Yes.
lot about the divisibility tricks. And
Yes.
I actually kind of like that, we started off pretty straightforward, and then by the end of it, things got a little bit more complicated. We started getting
Yep.
into some of the proofs and stuff, which, is sort of meant to be a challenge. I'd love to maybe scale back and go to sort of a more intro level starting point that I
Awesome.
had in mind.
Awesome.
Are you ready for this?
Yeah, I'm down.
So let's start with a nice blank page. And so what I want to do is we're going to think
Yes.
about the natural numbers, right? And by the natural numbers, we mean the counting numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way down, right? And
Got it.
that set of numbers. And
So
what
we're
we're
not
going
counting
to
zero.
do,
Sorry.
we are not counting zero. That's a very important distinction.
Okay.
Some people do include zero as a natural number. In my classes, we consider that a whole number.
Yeah.
And since we're talking about division, we're not going to talk about dividing by zero right now. but
Got it.
maybe
Awesome.
maybe it'll come up. Maybe we'll find a way into it. But I actually what I want to do is I want to do a little analogy as we think about these numbers. And so I've not done this one before, but a lot of the times, if you look at some of the stuff that I draw, I like to draw
Yeah.
this little number 10 with the crown on it. And I'm actually thinking about getting some stickers made up with this little icon on it for a education conference that I'm going to in a couple months. But
That's awesome.
the crown is supposed to sort of represent, we're going to talk about this idea of royal numbers. And in my research, I call them basic numbers. And when we say basic, I don't mean like easy. We mean basic in the terms of like of the base.
Like fundamental.
Yeah, more like in terms of, we have this base number that we have. We use a base 10 numbering system.
Yeah.
And so the basic numbers are like the numbers related to the base that are fundamental to what prime factors make up that base. And so we're going to think of these like royal numbers, right? So the idea is that some numbers have certain patterns that are just better. And so that's why we sort of think of them as being the royal ones. And the most royal number will be the base. And that's what we sort of indicate with the little crown and everything. It's like, that's the number that wears the crown or sits in the throne. If you want to call it the king or the queen, whatever terms you want to use. 10, and again, we use a base 10 numbering system. So I'm going to switch. I'm going to do everything in base 10 first. But the idea is you can actually think about any number as your base, whether it's base 12, base 60, base 2 for binary. There's all these other options that we can pick. For now, we'll stick with base 10. So the most royal number is the base, is 10, right?
Yes.
And so again, I'm just going to throw that little crown on there. And when we say that 10 gets the best of everything, what do we mean by that? Well, if we think about even just multiplying by 10, how do you multiply a number by 10?
You add a 0.
You add a 0. And it turns out if you change bases and have a different base number, that base number, when you multiply by it, you just add a 0 because it's actually the same notation. This is what, in any base, the base always gets this 1, 0 notation because what we're saying is 0 ones and then 1 base, right? So in base 10, it's 10. And then, 2 tens is 20, whatever. But so this is like ones place, and that's the base place. So base, easy to multiply by. How do you tell if a number is a multiple of the base? Or in other words, what's the divisibility trick for 10?
If it ends in 0.
If it ends in a 0. So you look at a number and you go, that number that ends in a 0, therefore it's divisible by the base. And in fact,
same thing you add, same thing,
Exactly. And the number of zeros on the end of a number tells you how many times the base will divide into that evenly. And so just by looking at the number, you get you can tell everything about whether or not it can be divided by 10. Does that make sense so far? And so that's why we say it's the most royal, it wears the crown, sits on the throne, whatever term you want to use.
So funny. I have like a fake crown in my
Do you?
look.
Yeah, we should get it out.
Ta-da.
There you go. Oh, that's perfect.
I'll be the base.
There you go.
No.
You'll be the base. And so we've got the base number. That's the most basic of the numbers. What other numbers do we think we're going to include in this? Again, we're taking the natural numbers. We're dividing it up into a few different groups. The first group are these royal numbers, the basic numbers. What other numbers do we think might be basic? Any guesses?
I have 2 guesses. One is the number that is half the base, which is 5 for us, right? And the other one is the 1, which is the, I don't know, the base minus, I don't know, just whatever the first one is.
So the number 1, you mean?
Yeah.
We're going to come back to 1 because I'm glad you said it. It has something interesting going on. But I love what you said about taking 10, dividing it by 2, and we get 5. Right. And so actually what we're going to say is more numbers that are basic is we're going to include factors of the base. Right. Which, as you said, in base 10, our 2 factors of the base are 2 and 5 because 10, 2 times 5. And so we're going to think of 2 and 5. Typically what I'll do when I'm doing my sketching and my sheets is I'll actually use like a light blue for 2. Again, the color blue here does represent that it's basic, and the colors will sort of mean something as we go through some of this stuff. But quite often I'll use a light green for 5, just to contrast the blue and the 2 and the 5. They're both sort of like these royal numbers. These are like the royal factors. Okay, and so any factors of the base, and it's really interesting what you said there actually about like we take the base and divide by 2. Well, actually, if you use an odd number base, like if for some reason we're using base 11, suddenly all the rules for 2 that we're used to go out the window. Like odd numbers, even numbers no longer end in even and odd digits. Like it really actually messes things up. So if anyone's interested, play around in odd bases. But we're going to say that 2 and 5 are also part of this royal set of numbers because they're factors of the base. And again, if we think about what's the divisibility trick for 2?
All the factors 2, 4, 6, 8, 0, if it ends in any of those numbers.
Exactly right. If it ends in a 0, a 2, a 4, a 6, or an 8. And if you think about that's the same as the divisibility pattern that the base gets, right? 10, you look at the last digit, but it's easier because you only have to check to see if it's 0. So 2 and 5 get this same royal trick, but because they're not the base, they're like the prince or the princess, however you want to say it, but like they still get the best trick, but it's not quite as good as the actual base, right? You still only have to check 1 digit on the end, and that tells you whether it's divisible. It's just that for 2, you now have to check 0, 2, 4, 6, 8. For 5, if it ends in a 0 or a 5.
Yep.
So there are 2 options there. So does that sort of make sense how it's all the same divisibility trick? 10 just gets a slightly better version of it.
It gets the easiest one.
Yeah, exactly right. And then so the factors of the base sort of get like the same one, but maybe not quite as good. And then the next one, the next sort of group of numbers here are basically the powers of the factors. Of the base, which I'm not going to write. But again, factors just mean a number that divided the base evenly. And so when we think about what are the powers of the base, or the factors of the base, well, we have like 2 to the first power is just 2. And then we have 2 squared is 4. If we multiply by 2 again, we get 8. That's 2 to the third, 16, 32, all the way down, right? So those are powers of 2. We also have like 5 and the powers of 5. Do you know, let's see, most people know
25, 225.
Yep. Not 220,
5.
No, 125, right?
1.
5, because you have 5 quarters, would be $1.25.
Yeah. Okay.
Yeah. The next one is 625, which is 5 to the 4th power, and then I think the next one ends in a 25. What is it? It's
no.
3125. I think somebody check that. I might be wrong. The point is, right, we have these sort of powers of 5. Also, the powers of 10 itself, right? What are the powers of 10? Easy to do. 10, 100, 1,000, right?
Yeah.
And if we think about how do I tell if a number is divisible, for example, by 4? I don't know. I think we mentioned this one briefly last time.
We get the last 2 digits of a number, right? And then we...
Yes. You look at the last 2 digits of the number. And it turns out the same thing is true for 25. If you count by 25s, 25, 50, 75, 100, 125, 150, 175, 200, right? It'll either end in 00, 50, 75, or 00 again. It'll only end in 4 possible things. You just have to look at those last 2 digits. And so if the last 2 digits work, so for 4, which is the power of 2, the second power, you have to look at the last 2 digits. For 25, you look at the last 2 digits, and 25 is 5 to the second power. How would you check if a number can be divided by 100? What would you look for?
Last 2 digits, 2 zeros.
If the last 2 digits are 2 zeros. And so there's sort of like a connection here. And I have a drawing of it here somewhere. And so this is sort of just, the things that I'm constantly thinking about and sketching out and working on. Let's see. So again, we've got 2 to the first, 2 to the fourth, 2 to the 8th, or 2 to the third is 8. Powers of 5 over here. And maybe this isn't the easiest to read, but A number is divisible by 2 if the last one digit, right? The last one digit. For 4, it's the last 2 digits. For 8, what do we think the divisibility trick for 8 is going to be?
The last
you look at
3 digits?
The last 3 digits. And the same pattern holds for powers of 5, right? 5, you look at the last one digit, if it's a 0 or a 5. For 5 squared, which is 25, you look at the last 2 digits, the last 2 digits being a 0, 0, a 2, 5, a 5, 0, or 75. And then again, if you wanted to create a divisibility trick for 125, that's 5 to the third power, you look at the last 3 digits. So we see there's sort of a pattern here.
Yes, for sure.
Does that make sense so far where we're headed with this?
Quite interesting.
Yeah.
Mysterious.
And again, it works with powers of 10 as well. We would do the same sort of thing. Right. So we have our set of royal numbers. We have the base itself. We have all the factors of the base, all the powers of those factors. And then basically the last group that we're going to throw in here is all multiples of royal numbers. And maybe I should have written that in gold, but basically any of these numbers that we've talked about so far, you can multiply any 2 of them together and that will give you another royal number, right? And so as a great example, if I were to take the number 4, which is a royal number, and the number 5, multiply them together, that makes 20. So now the question is, well, what is the divisibility trick for 20? How could I tell if a number is a multiple of 20 or not?
You check if both of the royal numbers are multiples, factors.
It's easier than that. If we think about it's going to be similar. It's going to have the same last digits trick.
Right. Okay.
Because if we count by 20, 40, 60, 80, 100, the pattern starts over again. 120, 140, 160. Yep. So what would it be?
If the last digit is 0 and then the digit before that is a multiple of 2.
Yeah. Or in other words,
2, 4, 6, 8.
We
0.
only have to look at the last 2 digits.
Yeah.
If the last 2 digits are divisible by 20, so like in 180, we look at the last 2 digits, it's 80. And so therefore that number is divisible by 20. And so if I wanted to throw a really big number out there, I could say, is the number 144,440? Can that number be divided by 20?
Yep.
Yes, because you look at the last 2 digits. The last 2 digits are 40. 40 is divisible by 20. And so therefore, it doesn't matter what digits come after that. That number will be divisible by 20 evenly.
Yep.
And so notice that 20, as its prime factorization, is 2 squared times 5. And again, because it has that power of 2 in it, it has the last 2 digits trick. Does that make any sense?
That does make sense. But here's a question.
Yeah, please go for it.
Write, instead of 4 times 5 equals 20, what if we write 2 times 10? It doesn't matter because we can still write it as 2 squared times 5, right?
2 squared times 5. We want to get it down to its prime factorization because we have to know how many powers of 2 it has and how many powers of 5 it has. And then we have to figure out. And so the last piece, if we wanted to say in general, what numbers are basic? And again, we're still working in base 10 here, but we're going to talk about when we're dividing by a number, we'll always use this little lowercase k. And so k is a basic number if it's of the form 2, and actually I wanted to do that in light blue, but that's okay. We'll get it next time. 2 to the n times 5 to the m. Right? Its prime factorization has only factors of 2 or factors of 5 or both. But no factors of 3, 7, 11, no other prime factors show up other than 2 and 5. And so then the question is, given a basic number, any basic number, what is its divisibility trick? And so now we've got n and we've got m, and we have to think about what do we think the trick is going to be if we know the values of n and m, right? If I give you a number like, 400, you find its prime factorization, you get the powers of 2 and 5. What do we think the trick is going to be for k?
Can I give a guess?
Please do.
Is it whichever number is the highest, n or m, and that number is going to be the number of spaces. Or
Exactly right. And so we look at what is the max of n and m, and whatever number that is, you look at that many digits on the end of the number. Now, there's one little caveat I need to point out here, because for the longest time, I thought that was the trick. It turns out this only works in base 10. If you try this in base 12, it won't work. There is a slightly more general, it's not quite that, but this is what it is in base 10. Does that make sense?
Okay. Yes.
And maybe if we have a little bit more time, we can explore something like a base 12 system and how it works. But for now, we'll leave that as sort of an exercise for the viewer, is play around in base 12 and see, does this still hold? And you'll find that there's a slight issue. But for now, working in base 10, given any number, k, if k's only prime factors are 2 and 5, then a number is divisible by k if and only if the last max of those two numbers is divisible by.
Perfect.
Does that make sense?
Yeah.
Perfect. And so that's our basic numbers. So again, this is numbers like 2, 4, 8, 16, 32, numbers like 20. Like you could take basically any numbers from these lists and multiply them together. So 16 times 5 would be 80, or 32 times 100, 3,200. Multiplying any of those numbers together. But now we know the divisibility trick for all of those numbers. And so we can actually, and I'll show you what the proof looks like, because I wrote it out the other day, and we won't maybe spend a ton of time here, but this is the general proof for if I assume any base b and I define k. K is such that if p is a factor of k, then p is a factor of b, meaning the only prime factors of k are the prime factors of your base. So it only has those prime factors. Whatever prime factors your base has, if k only has those factors, this is how you prove its divisibility trick. Basically, n is divisible by k if and only if k divides the last m digits of n, where we talk about m being like the max of the two numbers. There's actually a little bit more to it, but there you go. There's just sort of a quick preview of what that, and it's not long.
Yeah, and I love math and colors.
Isn't that great? And so like the different colors will start to mean things as we go through it. But the idea here, again, the question that we're really trying to think about is, given any number, what is its divisibility trick? Yes. And so now we've just solved that for a huge chunk of numbers. Any number that we're going to call basic or royal, again, that sort of means the same thing. The idea is a number is basic if its prime factors are, the only prime factors it has are those same prime factors of the base. And so that's the first group.
Yes.
Now we're going to move to the second type of numbers. And so if the basic numbers are the ones that only share with the base, what do we think the next group might be?
That share one factor with the base and one factor not with the base? That's
actually group 3. We're gonna actually look at the ones that have no common factors at all of the base. Okay, and so I call these ones coprime, and I always spell it wrong, coprime of the base. And the math people might recognize the word coprime has a meaning in math. Two numbers are coprime if they have no common factors. That's why we add this little like coprime of the base, meaning it's we're taking that number.
Like in
we're comparing it to the base number, and now we're saying that these numbers have, so these numbers k have no common factor with the base.
Like 3 and 7 in our case.
3, 7, what else?
Hold on, let me go through the numbers. 2 we got, 3 we have. 4 is a no, 5 is a no, 6 is a no, 7 is a yes, 8 is a no, 9.
9, 9's an important one. 11. Basically, any other prime number other than 2 and 5 will be in this list. But also multiples of those, right? So like 3 times 7 is 21. So 21 is included here because it's the product of two coprime numbers. Does that make sense so far? And so again, in sort of our royal analogy, these are kind of like the common folk. These are the ones that have no royal descendants or blood or anything like that. They're just the you and me of the number world. Does that make sense?
No crowns, no.
No crowns, no whatever. But two of these numbers do have a special property that, again, they're not royal, but they're sort of like, I like to say, like the right hand and the left hand, almost like Game of Thrones. Tyrion Lannister is the right hand to the king or the queen or whatever. Any guesses on which two numbers have special properties?
I feel like 11 is one of them.
11 is one of them, and the other one is 9. And so what is the divisibility trick for 9? If we remember from...
It's still the last two digits, right? We have to look at the last two.
No, this one has a special one.
Oh, okay. Something about adding. I feel like you were showing it to me last time, and I forgot.
The sum of digits trick. Meaning, if I have a number, the example I always use is 3,456. Can that number be divided by 9 evenly? To find out, you take the sum of the digits, plus 3, plus 4, plus 5, plus 6. That'll add up to 18. And because 18 is divisible by 9, 3,456
we did the whole proof of that last time.
Exactly right. Exactly. We proved it last time. And the reason we said that this works is because 9... Whoa, I'm knocking over my camera. I got too excited. 9 is 1 less than 10.
Yep.
That's the thing that you use to prove it. But it turns out that we can generalize that to any base, right? It doesn't have to be base 10. Whatever number is 1 less than the base gets this sum of digits trick. And it turns out this is going to be an important one. It's a special case, right? And in mathematics, we always look at like what's the general case and what is a specific special case. This trick for 9, there's a lot that we need to say about it. But for now, we're just going to think of this as like a special case. So that's why I think of 9 as like the right hand to the crown, right? Or the right hand to the throne. It's like the most, it gets, in terms of divisibility, it gets the best divisibility pattern for the numbers that get the worst divisibility pattern, right? So the royal numbers, they get the best of everything. These numbers get the worst of everything. But 9, because of its position, gets the best of being the worst, if that makes sense, right? This is the best trick for a number that is co-prime of the base. Is that so far so good?
Yes, following completely.
Perfect. Do you remember, this is the harder one, the divisibility trick for 11?
Do I remember it? No.
Yeah.
We have to take the last two, multiply by something.
Nope, you're thinking ahead to 7 and 13.
Okay.
This one, we briefly mentioned this, gets the alternating sum of digits trick. Meaning, and I should have had an example, right? I think the one that I normally use, actually, let me come up with a big one. Let's see. Suppose I had the number 13,574. And I want to know, can this number be divided by 11 evenly? The way that we check is we take the alternating sums of the digits. We start on the leftmost digit, which is the 1, and we make that a plus. And then we go, every other number gets a plus. So the 1, the 5, and the 4 are plus. Then the alternate digits, the other digits, the 3 and the 7, get the minus. And the idea is you take the sum of the positive numbers, so the 1, the 5, the 4. You take the sum of the minus numbers, the 3 and the 7. 1 plus 5 plus 4, 5 plus 4 is 9, that would be 10. And then you subtract,
minus 10,
which is 0. Does 11 divide 0 evenly?
It does.
It does, because all numbers divide 0 evenly. And so, yes, that is a multiple of 11, which means, yes, that is also a multiple. 11 is also a multiple of, or 11 is a divisor of 13,574.
574.
Does that make sense? And so these two here are our special cases in this. And so I like to say, again, 9 is like the right hand to the crown. left 11 is like the left hand, or maybe the Joker, the jester. It's got this goofy trick, but it works.
We're
And
building a
again,
whole kingdom. We can make like an entire Alice in Wonderland story with these characters.
exactly right. Exactly. Maybe that'll be our creative writing assignment at the end, once we've
Oh.
gone through it all. But yeah, so these numbers are like the special cases within the coprime. And again, 11 gets this property because 11 is one more than the base number.
Ah.
And again, that works if you change your base number. So if you're using base 12, well, now
That would be
13
13.
gets the alternating sum, and 11 gets the regular sum of digits trick. So depending on what base you're using, tells you which divisibility trick you get. Now, we talked about, and this is where things start to get a little bit complicated, because I was able to prove the trick for 9, and we briefly talked about the proof for 7 last time. The divisibility trick for these coprime numbers, and real quick, I'll review the trick for 7, because it's worth revisiting. And actually, I'm going to use a different one than the one I talked about last time. The last time I talked about multiplying by the last number by 2. This time we're going to use a slightly different one, and there's a very long reason why I won't get into. But how do I tell if a number can be divided by 7? And the number we want to check is 343. How do we know? How can we check if this number can be divided by 11? Do you remember it at all? I know you sort of do, because you mentioned it a few times. What we're going to do, you take off the last digit. So I draw the little line to indicate we're removing that 3, and we're going to multiply that 3 by 5. Okay. 3 times 5 is 15. And then what we do is we take that 15 and we're going to add it to the remaining digits. Yep. So we're sort of pretending like that digit doesn't exist anymore. And then we take 34 plus 15, which would be 49. 49 is, of course, 7 times 7, which means it's divisible by 7. And so because this number here can be divided by 7, 343 can be divided by 7. And it's like, oh, okay, well, why? Why is it that if you remove that last digit, why does this work? And again, we briefly took a look at the proof, and I'm not going to go through all the steps of the proof right now, but it's a good challenge problem. Where does this 5 come from? What is it about this number? And what it is, and I'll tell you, because again, I think we briefly, in fact, I think I even wrote it out last time, somewhere in here. This equation. Given a number k, so now we're talking about k being coprime.
To the base.
And every time I write an extra m there, I don't know why I do that. Coprime of the base. Actually, I do know why I do that. It's because the next one is composite of the base, and that does have an m in it. But basically, what we do is, given our number k, so in this case, our number was 7, we are trying to find a multiple of 7. That's m is the multiple. A multiple of 7 that is, what we're going to do this time is we're just going to look at one less. A multiple of 7 that is one less than a multiple of our base 10.
Right.
And so the multiple that we're thinking about here, a multiple of 7 that is one less than a multiple of 10. Any ideas? It's a weird thing to think about.
Multiple of 7 that is one less than a multiple of 10.
Yes. In other words, a multiple of...
Oh, wait, but 49, right? Because 50 is...
There you go. So what we do is we say 50 minus 1 is 49, which is 7 times 7.
I see.
And so the idea is, given this number, this is k, we want to find this number a such that it's one less than a multiple of 10. And this number here, we're going to call this the divisibility coefficient. It's the number that you multiply that last digit by, and then you add to the remaining digits, and that's your divisibility trick. And so, a second example, let's do 13. What would the divisibility trick for the number 13 be? We're trying to find a multiple of 13 that is one less than a multiple of 10.
39, so it would be 4.
Exactly right. So 4 times 10, 40, minus 1, that equals 39. And 39 is 3 times 13. So the divisibility trick for 13
is 4.
Is 4, right? So let's say I have the number 169. And I want to know, can that number be divided by 13 evenly? What we do is we remove that last digit, take off the 9. Let me move that up there a little bit. Multiply that by the 4, this 4. 9 times 4 is 36. And then we add. And 16 plus 36, that would be what, 252? Did I get that right?
Yeah,
and then,
yeah,
then if we realize that that is 4 times 13.
That one might take me a moment, but
yeah, so the point is this 52 is a
Yeah.
multiple of 13, which
Yeah.
makes this a multiple of 13. Now, if that's confusing to see, if we don't know for sure right away if 52 is a multiple of 13, well, we can apply the trick again. We can say, can 52 be divided by 13? How do I check? Well, you take off the last digit, multiply it by 4,
So we
and
got
then
8.
add.
And
5
then
plus
what
8
is 8
is?
plus 5? 13.
Well, that would be 13, which is definitely a multiple of 13. So because 13 is a multiple of 13, 52 is a multiple of 13, which means 169 is a multiple of 13.
Yeah.
And so this is how the divisibility trick for coprime numbers work. You think about this relationship, you know K, you find A such that, and again, when I first wrote it, I wrote plus or minus. For now, we're just going to use the minus case. There is actually you can actually use the plus as well. And then when I first started this project, I was using the plus because I thought that's what it's supposed to be. But it takes you down we're going to use minus for now. Okay. And so when I say what's the divisibility trick for coprime numbers, we're going to say I'm going to call it the method of divisibility coefficients, which sounds very fancy. It just means find this number A and then multiply that last digit and add, and that trick will always work. So again, you can pick any number that has no common factors with your base, and this trick will work. And it turns out that the tricks for 9 and 11, I mentioned they were special cases. They still actually follow this same idea. You can, and there's actually a whole section in the paper that I'm working on where we actually have to show that the B-1 thing and that this version of the trick are the same thing, because it's not trivial. Like what we're saying when we do the B-1 thing that we did for 9, the proof that we did in the last video, doesn't actually use this fact, this trick. But you can come up with, and in fact, maybe if we take a second here, what would based on this rule, what would the divisibility trick for 9 be if we were to think about just in terms of we're looking for a multiple of 10 that is 1 more or 1 less than a multiple of 9?
Well, it would be 9.
It would be itself, right? So 9, and I'll even put in here for emphasis, 1 times 9 is equal to 1 times our base number minus 1. And so our divisibility coefficient for 9
is 1.
Is 1. So you take off the last digit of the number, multiply by 1, and then add it to the remaining digits. And if you keep repeating that process, it's equivalent to just taking the sum of the digits.
Oh, I see.
But you have to prove that. It doesn't, the way that we proved the trick originally and the way that we prove it here are different.
Right. It's like 2 different flavors of the same exact thing.
Exactly right. It's one of those special cases, and there's actually a whole nother set of divisibility tricks that I call positional divisibility tricks that are based on what the number's location is by adding or subtracting from the base. These are what I call multiplicative divisibility tricks because it has to do with its multiplicative relation to the base. It just so happens that for 9 and 11, the multiplicative trick and the positional trick are the same trick. But again, we have to prove that. And so you with me so far? We still doing okay?
Yeah.
Perfect. And so those are our So we've got our basic numbers. These are like the royal ones. We've got the coprime numbers. These are like the, just the common folk. And then you already sort of said this. We're going to have a third set of numbers where we're going to use, if royal numbers are blue, and well, so this is going to be what you said a few minutes ago about
where one factor is like part of the prime factors of the base and the other isn't.
Exactly. So we've got the
Yeah.
blue numbers are the basic numbers. These are prime, they share prime factors with the base.
Yep.
The red numbers have no common factors with the base. And so the purple numbers are going to be called composite of the base. And again, the word composite already has a meaning in math, right? A number is composite if it has more than one prime factor. But so now we're going to say exactly what you just said. We're going to say a number k is composite if it has both a, so we're going to say basically has a basic factor, meaning a factor that is shared with the base, and you got it, has a coprime factor. As a coprime factor. So what numbers would be, and I did it again, I don't know every time. What numbers would be composite of the base? In base 10, we should say, yep.
So, okay, so let's take one of each. We have 2 times 7, 14.
14, I love it. 14 is a great example. And you're exactly right. We've got, that's 2 times 7. One base number, one coprime number. The one I was, yeah, go ahead. Shout them out.
You go.
I was going to say 6, right? 2 times 3. And I'm not going to do this for all of them, but 2 times 3. 12 would be another great example. 18 has factors of 3. Anything where basically what we're going to do is we're going to say that k, we're going to call it, it's TU factorization, where it's T times U.
Same thing with like 15, right? Because it would be 5 times
15 3. Is another fantastic example, right? And notice some of these numbers are even. So it's not that we're saying even or odd. Some of them end in a 5. So ending in a 5 is not enough to make you a basic number. Being even is not enough to make you a basic number. It's that you have only factors of 2 and 5. These numbers are sort of like, you know, maybe they're like the aristocracy where they've got a little bit of royal blood, but at some point in the line they married a commoner, right? And now they're a little bit of a mix of both. Does that make sense?
Exactly, yeah.
Yeah. And now, do you remember what we said the divisibility trick for 6 was? It's not very exciting.
Is it one I mentioned before in the wrong case?
No, it is not one that we mentioned before. And this one, I'll just tell you because it's, again, it's kind of boring. A number is divisible by 6 if it's divisible by 2 and divisible by 3.
Yeah.
That's the only check that we've got. So basically can be divided by 2 and 3, right? So the number has to be even, and the sum of its digits have to be divisible by 3. And we forgot to mention, I should have mentioned this on the last, when we were talking about the sum of the digits trick for 9. 3 also gets the sum of the digits trick because 3 is a factor of 9. And so in these two special cases here for 9 and 11, any factors of these numbers get the same trick. But it doesn't necessarily work for other numbers. And it doesn't work for powers or anything else there either. And I should have said that before. But basically, 6, how do you check if a number can be divided by 6? If 2 goes in and if 3 goes in. If it's even and the sum of the digits. How would I check divisibility for a number like 12?
Also 2 and 3, no? Because, well, I guess I'm not sure. 4 and 3?
In this case, we have to check, can it be divided by 4?
Yeah.
And by 3. And a lot of times people say, well, what about, can it be divisible by 2 and by 6?
Well, but then you're doing the same thing for 6 where you're checking if it's divisible by 2 and 3.
And if you think about the number 18, 18 is divisible by 2, and 18 is 3 times 6. So 18 is divisible by 2 and 6, but not by 12. You have to break the number down into its coprime part and its royal basic part, right? And so that's why we say here T is the basic part and U is the coprime part. And then the trick is, well, if it can be divided by T, whatever T is, so in this case T would be 4. And if it's divisible by U, the part that's coprime, then it's divisible by that. And so for these numbers aren't really that interesting. Because all we're going to do is we're just going to break it into its basic part and its coprime part, and then we just ask, well, what's the trick for the basic part? What's the trick for the coprime part? And so really, just by studying the first 2 cases, the red and the blue, tells us most of what we need to know about purple. Does that sort of make sense?
Interesting, interesting.
Perfect. And so from here, we now have 3 divisibility tricks. And you can prove those 3 divisibility tricks. And now you have a divisibility trick for any number, because all natural numbers will fit into one of these 3 groups. Make sense?
It's great. The universe loves threes.
Yeah, it does, right? And there's going to be a couple more 3s that come through here in just a second. So you're absolutely right there. One thing I want to mention is you talked about 1. And the question is, which group
does 1 fall into any of this?
Should we consider 1 a basic number because it's a factor of the base? Because all numbers are divisible by 1, so 1 does divide into the base. Do we consider 1 co-prime to the base? Because the greatest common factor of 1 and the base will always be 1. And so it is always co-prime, right? It has no common. So technically, we could make the argument that it falls into either.
Or we can make the argument,
And the thing is, as we talk about the divisibility trick, it's not that interesting. Because technically, the number 1 satisfies any divisibility trick that you can think of. If you say a number is divisible by 1 if, you can put anything after that if, because all numbers are already divisible by 1. So a number is divisible by 1 if the sum of the digits is divisible by 1. A number is divisible by 1 if the last digit or the last million digits. It doesn't matter what you say after that if, it's always divisible. And so for now, it's actually not that interesting of a question. But in a second...
It's not. Go ahead. It might not be as interesting, but maybe metaphorically it's interesting because it's like the unified field. It's like
and there's a few other things we can say, but we're going to circle back to that idea in a minute. And in the other part of it, suddenly that question becomes very interesting. So it goes from boring to interesting pretty quick. And so, sort of in my story, right? I was sort of telling this last time. I was just getting back into math. I had basically finished my master's degree, worked at a career in data analytics. I was always sort of tutoring sort of behind the scenes. And I decided to start really tutoring heavily again during the pandemic because it was like people are going to need virtual education options. I might as well start something for myself. And the very first students I worked with, all of the students, actually, I should say, anytime I work with new students, the first thing I teach them are divisibility tricks. Maybe not to this level, but just the basic ones for 2, 3, 4, 5, 9, just a few of them, just to get the idea of breaking numbers down. And so I challenged myself to go through and start proving some of these things. And I was trying to figure out, like, what is the general case? And so this was the point that I got to. We have these 3 groups of numbers. I didn't have any of these names or colors or anything. It's just basically recognizing that if it's 2 to a power times 5 to a power, it gets 1 trick. If it's not that, it gets another trick. And then if it's a combination of those 2 things, then it's just the 2 pieces, right? So those 3 tricks. And I was thinking, like, I definitely feel like there's maybe something more that needs to be said here. Not really sure what it is. And then I'm thinking about these 3 groups, and it just clicked. And that's so often how sort of math goes, is that these 3 groupings that we just described here actually come up somewhere else in math. And the question is, and I'm throwing that out there, and we're going to explore what that is and how it's connected. And the idea is, do you know, or should I tell you?
I feel like I saw you talking about this before. It was there's factors and then was it long division?
The long division comes in right at the end. That's the thing that ties everything together. And so that's sort of like the answer. So what I'm going to do is I'm going to bring us back to this page here that we saw a minute ago, where we looked at 2 to the first is 2, 2 squared is 4, 2 to the third is 8. And we saw that there's a pattern here with the divisibility tricks. A number is divisible by 2 if the last 1 digit is divisible by 2. And for 4, it's the last 2 digits. And for 8, it's the last 3 digits. And the same thing works for 5. Now check this out. If I take the fraction 1 over 2, what is 1 over 2? What is 1/2 as a decimal?
0.5.
0.5. And first of all, notice the blue and the green, right?
Yeah.
1 over 2 is 0.5. That's not a coincidence. But what we're interested in is looking at, well, what type of decimal is this? We're going to call this a 1-digit terminating decimal. Terminating meaning it stops. It's not one of those funky ones that goes on forever. It stops after a certain number of digits, and it stops after 1 digit. What is the fraction 1/4 as a decimal?
0.25.
0.25, which is a 2-digit terminating decimal. And then what is 1/8? 0.125, which is a 3-digit terminating decimal. So it seems like there's a connection between what power of 2 it is, tells us not only what the divisibility trick is, but what decimal pattern it potentially has. And so we have this idea of a terminating decimal, a number that stops after a certain number of digits. And we can see the same pattern holds over here for 1/5, 1/25, and 1/125. We get a 1-digit terminating, a 2-digit terminating, a 3-digit terminating. And notice that it's a 2, a 4, and an 8, a 2, and a 4, and an 8, and that they're complements of each other.
Crisscross. What? Did you see that, right? Like the 2 matches with the pairs up with the 5, and the 5 pairs up with the 2. That's interesting.
When we take the inverse of 2, we get 5. And when we take the inverse of 5, we get 2. And when we take the inverse of 25, we get a 4. And when we take the inverse of 125, we get an 8. And that's because in terms of the base, they are like base inverses of each other, right? They're the opposite. And again, I would encourage anyone who's interested to explore these patterns in base 12. But so we have this idea of a terminating decimal. We're going to focus in on that idea for a second. So we've got terminating decimals. What other types of decimals come up when we think about decimal numbers?
We got the repeating ones where it's the same number repeating over and over, like 0.
Exactly right.
3.
Yep. And any others you can think of?
We have one where they repeat, but in a pattern. But I don't know any of those off the top of my head.
Perfect. And then the last group.
Completely irrational, or we don't know.
The irrational numbers.
3.14, 159, something,
you
265, followed by who knows.
And so what we're going to do. Yeah, exactly. It goes on forever, right? We're going to say that there are 4 types of decimals. Okay. The first type are the terminating ones. Terminating, meaning they stop. And so we've already seen a lot of examples here. 1/2, 0.5. And it doesn't matter how many digits it has, right? You could go 1, 2, 3, 4, 5, 6, 7, 8, 9, right? But the point is eventually, as long as it stops somewhere, we're going to call it terminating. So far, so good?
Yep.
The second type, we're going to call these fully repeating. And what we mean by that is basically they repeat, but all the digits
are the same.
Not even that. It's the same repeating pattern. So the first example you mentioned was like 1/3, which is just 0.3 repeating.
Right.
Now this one, and last time I talked about my old boss, Lori, who taught me everything that I know about math. And one thing that Lori always said is that, or she always expected her instructors to know what is 1/7 as a decimal and to always teach it to the kids. And I'm so glad that she did that because it came up here. Any ideas? Do you know what the pattern for 1/7 is? Most people don't.
Off the top of my head, nope.
Nope. And so what it is you take the 7 and the decimal, you double the 7. 7 doubled
14.
Is 14. 14 doubled is 28. And then the last 2 digits, we expect it to be 56, but it is actually 57. And there's a lot to talk about here, but it's those 6 digits repeating. So it's 0.142857, 142857, 142857. It's the same 6 numbers that repeat again and again and again forever. And there's a lot to talk about. Again, like it has this interesting doubling pattern. It seems like it doesn't work because it's the 7 and not the 6. Like, why is it a 7? Why is it not a 6? And then you can start asking, well, why does it have that doubling pattern at all? What's so special about 1/7? And actually, it's a really big rabbit hole that has nothing to do with what we're currently talking about, which is the pattern itself. What we care about for right now is less about the value, more about
the type of decimal.
Exactly. So we're going to say that 1/3, 0.3 repeating. This is a 1-digit repeating or fully repeating. And then 1/7, we would call this a 6-digit fully repeating. Okay, and so these are the ones where all the digits repeat. But again, we can sort of have a hybrid of these two things that we're going to call partially.
Where like the first number is one thing and then it starts repeating after.
Some digits do not repeat, but the rest do. And so the example for that one would be 1/6. The fraction 1/6 is the decimal 0.166666666 on forever. But it's only the 6 that repeats. And so we would say that this is a 1-digit terminating, 1-digit repeating, partially repeating decimal. Does that make sense so far?
Yeah, and I see you're choosing these colors quite intentionally with the blue and the red and the purple.
Well, exactly right. Now, there's one more thing we need to mention here, which are the irrational numbers. We're not going to spend a lot of time talking about these guys right now, but technically we should mention this is like the 4th type of decimal. These are the ones with no repeating pattern. And it's important. No ending, right? They never stop and they never repeat. But the repeating pattern is important because some irrational numbers do have a pattern. It's just not a repeating pattern. And so the example of that would be the number 0.101001000100001 on and on forever. There's a pattern there. We're just adding an extra 0 between each one. But that's not a repeating pattern. When we say repeating pattern, it has to be the same block of digits that are repeating. And so, and as you said, we've got numbers like pi, 3.141592657, whatever, that goes on forever, right? Those are our irrational numbers. We're not going to touch these right now, although, again, maybe at the end they'll come up in a surprising way. But notice we've got these 3 types of decimals. And as you mentioned, we use the specific colors because which numbers have a terminating decimal?
The royal numbers.
And only the royal numbers. Exactly right. So if your denominator, if your fraction 1/k, and for now, we're only going to talk about unit fractions. This works for non-unit fractions, but by unit fractions, just meaning the numerator is 1, right? Okay. But if your number 1/k, if k is a basic number, if it's one of those royal numbers where its only prime factors are 2 and 5, it will terminate. And the number of digits after which it terminates is equal to whatever the largest power of 2 or 5 shows up in its prime factorization. And so here we can see that there's a connection between which divisibility trick it gets and which decimal pattern it has. And it's very explicit for terminating. We can see very clearly, like for 2, we check the last digit and it's a 1-digit. So like how the decimal pattern shakes out and how its divisibility trick, very clear, obvious connection there.
Yeah.
It gets a little bit murky when we start talking about like, what was the divisibility trick for 3? Well, it was that sum of the digits trick, right? So what does it being a 1-digit repeating decimal, what does that have to do with the sum of the digits divisibility trick? Not obvious. The trick for 1/7, we took off the last digit, we multiplied by 5, added to the remaining digits. What does that have to do with 1/7 being a 6-digit repeating?
5
and again,
plus 1. I don't know.
That's a good guess. It is not that. And actually, I originally used the trick where you take off the last digit and you double it. And so I thought maybe it had something to do with the doubling pattern. It has nothing to do with any of that. And so again, it's not clear. It's not clear at all if it's just, that only these ones have a deeper connection. Not at all clear about these ones. We're going to talk about these ones mostly. Real quick, talking about the partially repeating. When we look at 1/6, had 1 terminating and 1 repeating. Well, again, if we think about what multiplies to make 6, 6 is 2 times 3. And so 2
terminating number and 1 repeating.
2 gets 1 terminating digit and 3 has 1 repeating, exactly like you said. And so the fraction 1/6 gets 1 terminating decimal and 1 repeating decimal. So there is a connection between which decimal pattern this one gets and these decimal patterns. And again, all we're doing, kind of like we did with the divisibility tricks, is we just said, well, check for 2, check for 3. And so if I want to know what, for example, what decimal pattern would the fraction 1/12 have? We're not so interested in what its value is, but what pattern would we expect it to have, knowing that 12 is 4 times 3. So what decimal pattern does 4 get?
terminating.
How many digits?
2.
2, because it's 2 squared, right?
Yeah.
And so what we're saying is that the fraction 1/12 should have 2 terminating digits, and then because it's got a power of, or factor of 3, it should have 1 repeating. And sure enough, 1/12 is 0.8333333 on forever. I'm sorry, I messed it up. 0.000, oh my God. 0.083, and then the 3 repeats. So the 0 and the 8 are the terminating digits. Those ones don't repeat, and then the 3 repeats on forever.
If the 3 was like a 9, right, and it would be 3 squared, would we have 2 repeating digits?
And that is such a great question. And this is something I wanted to mention earlier about the divisibility tricks. I didn't do a great job. Why does 3 get that sum of the digits trick? It's because it's a factor of 9. And so it's actually 9 that gets that divisibility trick, and it's actually 9 that gets the 1-digit repeating pattern. It just so happens that because 3 is a factor of 9, it gets that trick. So your question of whether would that work, like maybe we could then say, well, does 27 get that pattern? And it turns out there is a way to predict it, but it gets quite complicated. And in general, the answer I'm going to give you for now is no. It actually has a lot of contributing factors. But I want to real quick let's talk about nines real quick. So if I have the fractions like 1/9, 2/9, 3/9, 4/9, 5/9, etc., what are the decimals here? Do you know this one? How do I convert these to a decimal easily?
The first one would be like 0.18, right?
No. It's a good guess.
0.1. Oh, 0.1111111.
0.1111111. It's just 1 repeating forever.
0.2.
0.2 repeating. 3/9, which we can recognize as 1/3, is 0.3 repeating, 0.4 repeating, 0.5 repeating. And so 9 gets a very special case where 9 is the denominator that gives you a 1-digit repeating decimal. And only denominators of 9, except for in the case of something like 3/9 that reduces to 1/3, because 3 is a factor of 9, 3 also sort of inherits that property from 9. And I don't know if you know this one. If I have something like 23 out of 99, so now instead of having a denominator of 9, now I've got 2 9s.
Right.
This is 0.23 repeating. And if I have 123 out of 99, that's 0.123, 3 digits terminating. So there's something about...
out of 999.
999, that is what I meant. Thank you. Yep.
Yep.
And so the number of 9s in your denominator tells you about how many repeating digits it's going to have. And there's sort of a more general idea here that gets, again, some of this stuff starts to get a little bit crazy, but the number of 9s, basically, if a number if I have the number 9999 that's made up of a bunch of 9s, any number that is a factor of this, if I do 1 over that number, it will be that many digits repeating. So like, and 11 is a great example, because if I have something like, what would the decimal pattern for 1/11 be? How could we leverage? Well, it's the alternating divisibility trick, but if I notice 1/11 as a fraction, I can write this as being out of 99.
Right, 9/99.
9/99, which means that this decimal is 0.09 repeating. And so any denominator of 9 gets 1 digit repeating. Any denominator of 11 gets 2 digits repeating. And then, so this is related to the fact that 9 and 11 are special cases. But again, we sort of have this question of, well, what's the general, like, how does this all fit in with these divisibility tricks? How is it that we take the divisibility trick for 7, which take off the last digit, multiply 5, what does that have to do with it being a 6-digit terminating decimal? right? And so this was sort of the point that I was at in my research of like, I recognized that there was this connection between these two ideas, right? Because we can break them out in the same way, but it wasn't clear to me what that connection was for these fully repeating numbers. And real quick, I'd love to show you, this is the Elementary Number Theory, fourth edition, Number Theory and Its Applications by Kenneth Rosen. So this was the number theory book that I used as an undergrad. And for the last 9 months, we've been traveling around Washington State. This is one of the only math books I brought with me because it was so important to this research project. And so in chapter 5, section 5.1, Professor Rosen tells us about the divisibility tricks. I don't know if you can read that there. And then in chapter 12.1, he talks about decimal fractions and what patterns they have. And so he goes into quite heavy, actually, all of the theory behind how do you tell which fraction gets which decimal, all that stuff. But nowhere does he ever say that the divisibility tricks are connected to the decimal patterns. In the chapter 5.1, he just sort of goes, oh, well, we've got these divisibility tricks. It's just a modular arithmetic. It's remainders, whatever. That's all he really says about it. It's just one little section and then he's done. And then he goes into this huge amount of detail. There's this theorem. It's theorem 12.4. It gets, like, I'm still sort of working through it. It's so complicated, but it goes into how you tell and how you prove each one. And so it's like, why have both of those things in your book, but not talk about how they're connected? And so my question was, well, how could I better understand the divisibility tricks for this number, which for right now, again, this is where we're using this trick here, this find the multiple. So how is this divisibility trick connected to what decimals? And the bigger question is, by understanding how fractions convert to decimals, can we find a better or a more general divisibility trick than this? And so that was sort of the big question that, like, I was working my data consulting job. Basically, I had a data consulting business. I was on this big project. I got super burned out, didn't really want to go and find another client for my consulting business. And this question was the thing that, like, my ADHD brain wants to focus on. The thing that's distracting me is this question. So, like, when I'm waiting in line at the grocery store, when I'm driving, when I'm supposed to be working, this was what I was thinking about. And at some point I just thought, well, why aren't I just working on this? Because if this is what my brain wants to do with its time anyway, why not do this full time? It's like, well, how could I possibly do that? And the answer is I should start really teaching more virtually. And so that's why I decided to sort of pause my consulting business and go full force into, I'm going to be a virtual math educator. I'm going to work with adults. I'm going to do this. Because the more that I teach, the more that I sort of get to work on, think about these problems. And the idea was, well, I'm going to create courses and stuff that tie all these things together. And so that's sort of how I got from here to there. But it was only last summer, and really, I mean, I'm still sort of working on it. It was only the last maybe 6 months that the clear picture emerged and everything fell into place. And the answer to the question, can we find a better divisibility trick, is yes. And is it connected to how fractions convert to decimals? And the answer is yes. And it turns out, how are these two things connected? They are the exact same thing. It's not even that they're similar. It's not that they satisfy the same criteria. These two concepts, how the divisibility trick works and which fraction 1 over that number gets, are the same thing. And so, what do you think? Is that exciting enough?
Totally. I mean, same thing.
And it took me forever. It took me 6 months to figure this out, and I was really sort of seriously working on it. And it's funny because I'll keep going with story time for a second, because so at this point, Kayla and I, we had sold our house in Denver. We're now living out of a Sprinter van, traveling around the country, and I was working on these math problems as I went along. And at some point I got so burnt out by it, I decided I was just gonna start taking SATs just for fun, just to do something. But fast forward a little bit, we decided we wanted to go to Seattle and Washington State. And we had no idea how we were going to make it happen, like where we were going to stay, what we were going to do. All we knew was that Kayla's friend Ashley, her birthday was coming up. So we wanted to go up and celebrate Ashley's birthday, and then we would figure it out. We had sort of no plans. And when you start traveling, and maybe you've experienced this, Janet, is things just start to line up and work out the way that you wanted them to. And so what it was is Kayla really wanted to get into like tour guiding and like, maybe she could do that as sort of a job. So she called somebody that she knew, this guy, Tom. We have our own podcast where we talk about our travel lifestyle and how important Tom was. So go check that out if you're interested, because there's this whole story about how when we first got the van, all this stuff. Anyway, we called our friend Tom, and Tom said, well, I don't have any tour guiding work, but maybe you'd like to work this job I'm working at the Seattle airport. And all it was is basically we would be the people that hold up the little sign with the name on it. And, you greet these CEOs as they're coming out, you get them in their car, they go off to their conference, whatever it is, and then you get paid like $45 an hour just to stand around in the airport for 3 days. And it's like, that sounds great. So how it connects to all of this is I was sort of, basically, I picked up my one VIP. The next person wasn't arriving from Germany for another 6 hours. And there was nothing else to be done. So the guy just said, just be ready 6 hours from now to pick this guy up and do whatever you want. So I was sitting at the Seattle airport. I had a clipboard with a blank sheet of paper, and I was trying to figure out this problem exactly of, is there something more that we can do here? And I didn't answer that question, but what I did come up with is I was playing around, and at this point, so anytime I wanted to know, what is 1 over some number? Obviously, the fraction 1/7, we had that nice little trick where it's like, if I have 1 over 7, we can just use sort of that doubling trick. And we get that this decimal is 0.142857, which again, we could probably do a whole separate video on just that. There's a lot of interesting things here. But so anytime I was doing the long division to figure out what these decimals were, I was always doing it the way that I was taught in elementary school, where it's like, you take the 7, you put it on the outside, you draw the weird little thing, and then you put a 1 on the inside, and you go
dot, 0.
There you go. And then so by the time you divided it out, it's like this long, and you've got all these numbers written out. And like, I was doing that, like I was calculating 1/13, 1 over 141, like all of these different numbers to try and figure out what these patterns are. And I was screwing around with it. And what I came up with is a slightly modified way of doing long division. That was in that 6 hours I was getting paid to sit at the airport and do nothing. I started working on this problem, and I came up with, and I remember because I posted on a picture of it on Instagram, and the one person that followed me that was a math person was like, "Oh, that's really cool." And I was like, "Yeah, I did something, And so what it is, I'm going to show you this real quick. And are we doing okay on time? We happy to keep going?
Yeah, we're great. We're great.
So this is, and I should say that this is just long division. It's no different than this method, other than it looks slightly different. And so when I say that this is, and it's really sort of based on, if you take like a number theory course or something, we call this the division algorithm or the Euclidean algorithm. Like it's based on this idea. So what it is, if I want to find the decimal pattern for the fraction 1 over 7.
Yeah.
And again, and the nice thing about this trick is that this works in any base. And so if you really want to challenge yourself, start doing long division in different bases. It's a lot of fun. But what it is you take your numerator, right, the top of your fraction, and you multiply by 10, or multiply by your base if you're in a general base. And so 1 times 10 is 10. And then we just ask the question, well, how many times does 7 go into 10?
1.
1. And we say, so it goes in there 1 time with 3 left over, right? Remainder 3. And again, that's the exact same thing as 7 goes into 10 once, and then you subtract, and then you get the 3. We're just really, instead of using subtraction, we're using addition to just add back up to whatever the number is. But then the next step is you take whatever your remainder is, multiply that by 10, and you repeat the process. And so you go 3 times 10 is 30. 7 goes into 30 4 times, which is 28, with a remainder of 2. And then we take the 2, multiply by 10, and we say, well, how many times does 7 go into 20? It goes in there twice, which is 14, with a remainder of 6. Multiply by 10 is 60. 7 goes into 68 times, because it's 49, 56, with a remainder of 4. 47 goes into 45 times.
7 times 5 is 35, yeah.
With a remainder of 5. And then we go 50 7 goes into 50. It actually goes in there 7 times. And then we get a remainder of 1. And
So
when
we're
we get a
back
remainder,
to
we would be back. We would loop back up here and start here again. And then it would just be the same remainders. And notice that the numbers, where's purple gone? Oh, there it is.
the
The numbers that we get here
are the decimal.
1,4,2,8,5,7. And I thought, oh, that's so cool. So you can do this with 1/13 or whatever else. And all of those numbers there end up giving you that decimal pattern. And this is so much easier to write down than doing this stupid thing. And so I feel like I'm a little bit of a crazy person sometimes, because like when I'm sitting on a,
we're starting a revolution, new ways
yeah, but so now I'm at a point where I'm like doing this in all these different bases. My notebook is filled with these calculations of long division where I'm doing all this stuff. So I feel a little bit like a crazy person, but this is an alternative way of doing long division. And again, when I say I came up with it, I found this on my own. I'm sure this is nothing so groundbreaking. Like anyone could have really found this, but I thought it was just so cool that, okay, I've got this new method of doing long division. Fantastic. You know, it's just going to save me time. And so we wrapped up the job at the Seattle airport, and it was actually really cool because everything did work out. We ended up getting offered a 4-month house sit in Washington State. And so we worked for 3 days. We celebrated Ashley's birthday, our friend Ashley up there. And then Kayla and Ashley actually took our Sprinter van down to California. I got to live in Capitol Hill in Seattle by myself for a week. And then we went up to Sumas, Washington, and we lived in a house for 4 months. And like, that's how we made Seattle work. We actually ended up staying in Seattle for about 9 months, or Washington State, Pacific Northwest, for about 9 months, just bouncing around.
That's so funny. I was probably there at the same time as you
were.
Were
You really?
I was there last year.
Yeah, you probably
for like
were.
A good 4 months on some island next to Tacoma, and
oh, nice, yeah.
That's so funny. I literally came back to New York in like November, right before my mom's birthday, and then I've been in Argentina since this New Year.
There you go. Yeah.
Wow, that's so funny. We didn't even meet yet.
No, we hadn't, but we were probably there at the same time. That's hilarious.
Yeah.
I love it up there, though. It's so beautiful in Washington State.
Yeah, for sure. Yeah. It's like a city, but it's very calm, and
right.
It's nature is cool.
It's absolutely gorgeous. It's a little rainy, but then you get all that wonderful nature, and there's hiking, there's mountains, there's water, there's beaches, there's literally anything you can think of.
Yeah, and the weather's pretty stable. Like, it's raining, but it's not like freezing. You can just put on a rain jacket and go outside.
As soon as we got back to Michigan, it was like 33 degrees, and it's like, why are we here? It may not be rainy, but it's like cold and miserable, whereas Seattle is wet, but at least it wasn't cold all the time.
Yeah.
But anyway, so where we're going in the story with all of this is we started working these transportation type jobs. And if you're a nomad, if you're the type of person, you're an entrepreneur, you don't have maybe a stable income like we don't, we rely on these gigs, sort of gig jobs that we take all over the world, and like they pay really well, and it's a great option for anyone that's interested. But where we're going in the story is that, so a couple weeks later, now we were hooked on these transport jobs. And so now we were working for a different company. And what it was is I was at a hotel, and the job was people are going to come down from the hotel. They need to get on this bus, which leaves at this time. Just be the person that gets the people on the bus and count them. It's like such easy work. And again, we're getting paid like $40 an hour to do this. Wow. And then the bus leaves, drop them off, and they just said, okay, well, sit in the lobby of the hotel until we get back and just take a little break. So again, I'm getting paid for like sitting there for an hour. And I will say,
your own math research.
And exactly. So it's like I have my clipboard, I flip the sheet over, and I'm going to start working on stuff. And I will say that the lobby of the hotel was playing this incredible music. So if you're into dance music, EDM, all that stuff, like I am, the soundtrack to this portion of the video is the song "Treat" by Romparte, Romparte. Check that video out if you want a soundtrack. So this is what was playing overhead in the lobby of the hotel. And so the idea is, great, we've got this new method of doing long division. We've got this divisibility trick where we're using this MKAB plus or minus 1, where you remove the last digit, multiply, and then add. And so the question I was asking is, well, what if I had a really big number? And suppose I had a number like, just use a smaller example for now. If I have the number 86,415, And I want to know, can this number be divided by 7 evenly? Because that's the point of these divisibility tricks, right? Is can this number be divided by 7? And right now, the way that our trick works is we take off this last digit, we multiply by 5, 5 times 5 is 25, and then we add to the remaining digits. And so the question is now we get 8,666. Can this number be divided by 7? Well, I don't know. So we take off the last digit. And so it's like, for really big numbers, this last digit trick isn't that effective, right? You have to do a lot of time. So the question is, well, is there a way that we could remove more digits from this number and do something? And so now I'm sitting in this hotel and trying to figure out this problem specifically. And again, the what we have so far is that we're looking for multiples of our divisor. So the number we're dividing by is k, that is equal to a times b minus 1.
What? Any chance you can just add a 0? Like
Where?
times 50 and then instead of times 5?
Oh, that's an interesting question. And if we multiplied by 50 instead, well then
wait, no, we can't do that, but we can do a multiple.
It still has to satisfy this.
Okay.
And we should point out real quick, right? We said, earlier, if k is 7, then 5 times 10 minus 1 would be 49. Well, there are other numbers that you can use for here, right? It doesn't have to be 5. And it's not 50, but like you could find a bigger number that still works. And actually, it would be 13. 13 times 10 minus 1 would be 129, which is 129 divisible by 7. I realize that. No, I don't know. It's something. There's something where you can find other values of a. I should really have that down. But it turns out to be not super relevant. And so, again, I was thinking about this problem for like 6 months. It was a really long time, and not like full time. I still have work and life to do. But anytime I have a free minute, it's like, well, what is it? What is it? And it actually ends up being super obvious. At least it's one of those things in math where once you see the answer, it's like, why did it take me so long to figure out what it is? And so I'll tell you what it is, unless you want to make another guess.
Wait, let me think.
Yeah.
I think somehow we're going back to that whole where the number 1 becomes interesting again.
Oh, we should maybe have talked about that a second ago. Not quite that, but it is connected. And maybe that's where we can wrap up and we can see full circle, all that kind of stuff. What we're saying is that we know we can calculate this number a, where I can take off the last digit, multiply by a, and then that's the divisibility trick. And so the question is, could I come up with more numbers so that I could take off more than one digit and still have this work? And so the way that we define a is in terms of whatever our base is, minus 1.
Ooh, and exponents.
And it took me so long to figure this. So what we're going to do is we're actually going to say, we're going to call this m naught. And actually, m doesn't matter. And for those of us who are familiar with modular arithmetic, we can actually write this as like, we could also write it using this notation. K divides AB. Sorry, this is just a little aside here for those people who are annoyed that I keep writing M. We could also write using divisibility notation. So K divides AB minus 1. These two things mean the same thing. We're saying that there's a multiple of K that goes into AB minus 1 evenly. So there's that. That's the more formal version. But I'll stick with this for now. So what we're going to do is we're going to say, okay, this is like A naught. This is the first divisibility coefficient. But what if we were to then find a multiple of K that is equal to some number A1 times the base squared minus 1. And so again, I'm sitting in the lobby of this hotel. I've got my little power bar that I'm eating, and like suddenly this thought occurs to me. And in a similar vein to the proof that we did at the end of the last video with 7, you can actually prove that this works. You can remove more than one digit and use these numbers. We can define a sequence of numbers, which is equal to like A2 times B to the third power minus 1. And then we can go all the way up, dot, 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 M, we're going to call it M. What should we call it? I use L, which is maybe confusing. I don't know. I'm just going to say NM because it doesn't matter. The point is, it's, or maybe I should say I.
Some number.
I should say I there or something, but we use N for now. So it's basically like,
just any number you want.
yeah, times A to the N, yeah, AN times B. And we just have to know
plus 1.
N plus 1, exactly right, minus 1. And so now I'm feeling super powerful because like I proved that this worked, and it's like this is my second gig job that I've worked now, where I get some free time to actually work on this problem. I'm getting paid to do nothing and coming up with new math results here. And it's like the proof for this sucks. Actually, I was so excited because I do my sort of free sessions, and at the time I was doing a free Friday like proof session, and I had all these people that were coming to it, and I showed them this proof. I was so excited and went through all the details of it, and I absolutely lost them. They had no idea what I was talking about, and like, it was super complicated, but it works. And so again, if you want to challenge yourself to a proof, we're not going to do the details of this because it would be kind of messy. And honestly, I'm not even confident that I could prove it right now because it's really awful. It's a really, really awful proof, but it does work. And so now we've got these numbers, A naught, A1, A2, AN, and we have a method of calculating them. We just have to do the work. And so figuring out what these numbers are for a number like 7 actually gets really tedious. Because even like when I ask you, 7 times what number is 1 less than 10? We said it was 7 times is 5 times the 10 minus 1.
Is 50, and you have 49, but then you got
the 49. Think. And so now we have to think about, okay, what multiple of 7 is 1 less than a multiple of 100?
So...
And it's not easy. This is a hard question to answer.
Right, because... Well, okay, if we take... I'm trying to like think through it backwards. I'm like 7 times 100 is 700 minus 7. I'm just like, that's not going to work.
Yeah. And so what we could do, and the way that I actually did it, again, I'm still sitting in the lobby of this hotel. And so basically I just went, okay, well, let's do 100 minus 1. Let's do 200 minus 1. Let's do 300 minus 1. Let's go all the way through the list and just check. So it's like 99, 199, 299, 399. And this isn't too bad because you can just take off the last digit, multiply by 5, and you can figure out which one is it. I'm blanking now. I think it's...
Do I have a calculator?
And so the point is that doing it this way is doable. And I was at the point where like I was trying to figure out like for a larger number. So like when we start getting to higher exponents, it's like, well, what multiple of, we've got like 9999, and then 19999, and then 2999, and we have to figure out which one of these numbers is divisible by 7. And so it's very tedious, a lot of work, and I got through it. And what we came up with, and I wish I had it, I should have been a little bit more prepared. I could have written down.
Is there a pattern to what the A0, A1, A2 becomes?
Yes. And so I'll tell you. So what I came up with, and so I like to use this notation. I like to say, so like A, our set of divisibility coefficients, because now we had one divisibility coefficient. Now we have a certain number of them. And for 7, I was going through and I was figuring them out. And sorry, bear with me 1 second. I don't want to give it away is the thing. Shoot. So here I've got for 7, but that's in base 12. And you would think that for the amount of time that, like, I have the numbers memorized, and there's a reason why. I'm sorry. Where? Everyone take a quick breather because we've thrown a lot at you. What it ends up being is you get, the first one is 5, because we already saw that it was 5, and then we get 4, and then 6, and then, so 4, 6, 3, and so like I'm on the wrong, no, I'm not. When I'm saying that this is a 4, what we're
Yeah.
saying is that this number, 400 minus 1, 399. Is it 399?
Is
Hopefully, or else I look kind of silly. Yes, 399 is 57 times 7. And so 4 is the
right.
multiple of 100 that is, when we subtract 1 from it, ends up being a multiple of 7. And so it's 5, and then it's 4. And again, I'm doing all of this like manual
Right,
work.
right.
I'm figuring out these numbers. And finally, I realized that after a certain number, it went back to being a 5. It repeated. And I
Oh.
wish I had the sheet somewhere to show you the sort of all the handwritten notes. And again, there's a picture on my Instagram. Not that I ever go on Instagram,
If you
but
want,
there's.
we can, if you have the picture later, I can add like a link
Yeah,
so
yeah.
you can see in the bottom of the video. They'll just click on it if they want.
That would be perfect. And so what we've done, we've proven that these numbers existed. I haven't done the proof here. And now I'm starting to calculate them, and I'm getting the list. And I suddenly realize the numbers that I'm calculating here five, 4, 6, 3, 2, 3, 1. This long division process that I had come up with a few weeks beforehand, the remainders that you get, this is our A naught. That's our first divisibility coefficient. And then we get, this is the next one, and then that's the. And so when I say that long division was the answer to all of this, these divisibility tricks are simply the remainders that you get when you convert 1 over that fraction to a decimal.
Huh.
Let that sink in for a second, because it's
The
like.
remainders. When you.
So if I want to figure out the divisibility trick for 7, there's this more general trick. And I'll give you an example in just a second where we'll actually go through all the steps. But these A naughts we can calculate using the difficult method, or we can realize that it's simply just these remainders here. And then that gives us the more general divisibility trick.
Wow. Wait, do they repeat the same number? So like for 7, would there be 6 repeating A naught?
And that is the connection. That is exactly what it is. That because 1/7 is a 6-digit repeating number, the more general divisibility trick is that we can define a set of 6 divisibility coefficients that you can use to remove the digits of a number to determine if it's divisible by 7. And so, for example, 1 over 13, I don't even know what that is as a decimal because I don't have it memorized. It's 0.7623, but it's also 6 digits. And so 1 over 13 is a 6-digit repeating decimal. And there's a set of 6 numbers that you can come up with for the number 13 that creates a divisibility trick for the number 13.
Wow.
And so that's sort of that deeper connection that they're actually the same pattern. So I'm going to do one example, and then maybe we have just a few other small pieces to talk about, and then we can wrap it up. Does that sound okay?
Sounds awesome.
Okay, and so the number that we want to use, and we're going to do out the full thing here, but I had an example that I did before, and I messed it up a bunch of times, which means hopefully I won't mess it up this time. So let me just 721 357 245. Okay, so the question is, and again, we can prove that this method works for any number in any base. We're going to stick to base 10, but if we want to generalize, we could. So the number in question is 721,357,245.
Wow. Okay, that's a number.
And that's a nice big old number. And the question is, can this be divided by 7 evenly without a remainder? And so what this sort of method of divisibility coefficient tells us is that we can compute this set of numbers. And notice real quick that the remainders do not appear in the same order as and so that was the last piece that I had to figure out now that we see that these two lists of numbers are the same, you still have to prove that it's the same thing. So I call this the mapping problem. And I'm currently rewriting my proof of the mapping problem because I think I made some mistakes. But so it's like, why is it that they come out in different orders? that's a whole another question. But so we have this set of numbers. It's 5, 4, 6, 2, 3, 1 in that order. So we're going to write down, basically, the way that we come up with these numbers is exactly what we did here. We do this long division step, and we say, okay, so my set of divisibility coefficients for the number 7 in this case is 5, 4, 6, 2, 3, 1.
I have a question about that
Go
last
ahead.
one that says 1. Since it's the fifth one, does that mean that if you go 5 digits down and that number is divisible by 7 or something?
Not quite. That would be nice, wouldn't it?
That
The
would
way
be.
that, yeah, there's maybe something to that, and there's a lot to say about that 1 being there. That's actually the key to proving the mapping problem I just talked about was that. But so the way that the trick works
Yes.
is instead of just taking off the last digit and multiplying by 5, you can actually take off as many digits as you want from this number. And you can even go more than 6. We've got 6 divisibility coefficients, but the nice thing is you can reuse them.
Right.
You can take off as many as you want. And of course, I don't have, I would be a terrible professor because I don't have my notes like written out. And so here I took off, let's just take off 6 digits.
Yeah.
So we're going to take off 1, 2, 3, 4, 5, 6. Is that what I did? Sorry. Because I did it all right here. Yes, that is what I did. And so the idea is you take these digits off, and starting from the left, so you take your 3, your 5, your 7, your 2, your 4, and your 5, right? So that's just these digits. Rewrite them down here. You take your divisibility coefficients and you just multiply. So you do 3 times the first divisibility coefficient, which is 5, 5 times 4, 7 times 6, 2 times 2, 4 times 3, and then 5 times 1, because 5 is the last digit. And the idea is, even if I wanted to start with the 1 here, I would go 1 times 5 times 4 times 6 times 3 times 2, all the way down, and then you just go back to the start and you repeat. And so you can take off as many digits as you want, which is kind of exciting and whatever. So here we multiply. 3 times 5 is 15. 5 times 4 is 20. 36, 42. 4, 12, 5. And then we add all of these numbers together.
Okay.
Which last time I messed this up because I was doing it at a park and I didn't have my calculator. So 15
plus 5 is 20, plus 20 is 40, plus 42 is 82, plus 4 is 86, plus 12 is 98.
You crushed it. Well done. 98. And so what we do is we take the remaining digits, the 721, and actually in this case we're gonna add. Yep, 721 plus 98. And what do we get here? We get a 9, 1, 8, 1, 9. It's like, okay, well, I have no idea if that's divisible by 7 or not. And so let's repeat the trick. And now what we can do is we can just take off the 1 digit, multiply by 5. 9 times 5 is 45. And add, that's a 6. 8 plus 4 is 12. 162. Again, maybe not super clear if that's divisible by 7 or not. So let's repeat the trick again. And so maybe this isn't the best example because we still have to keep going with it. But we add and we get...
just move it, right? We can just move 5 over and start it at like the 2.
We could. You're absolutely right. We could have taken 1, 2, 6, take off the 2 digits, and then do 2 times 5 is 10. And then the 6 would be multiplied by the next number, which is 4. 12, 24, which adds up to 34. And then we take
135, and that we do know.
We add the 1, we get 35, and it works. Well done, Janet. That's awesome. And if we do it the other way, we get 42, which also works. You can see you can do it in any sort of order. So because this 126, this number here is divisible by 7. This number is divisible by 7, which means that number is divisible by 7. And so that is the general form of the divisibility tricks and how it connects to how fractions convert to decimals. Does that make any sense? What do you think about that?
I think that's amazing. I have never done division this way.
And that's the big irony, right? Is like I try to not teach my students long division at all because it's like I have a master's degree in mathematics. I don't ever use long division. Have you ever used long division in your life? No, of course
No.
not. We've got calculators and spreadsheets and we've got tools to do the division for us. But it's like I don't ever teach long division, and yet it ended up being like the thing to answer the question that I'd been pondering for all of these years. Is it just boils down to do one long division problem, you get that set of numbers, and then you're good to go. You can create that test. And so that's why, again, sort of all my little drawings and everything that I do, you see quite often. So here's again the 1/1/7. I actually got some laundry detergent on here, so it smeared a little bit. But the purple numbers, that's the decimal pattern. The numbers that are highlighted in gold, that gives you the divisibility trick. And this works for any number in any base. You can figure out what the divisibility trick is once you solve the last little piece, which is this mapping problem, which basically the order in which the remainders come out is not the same in the order in which you calculate the numbers when you do it based on the definition that we did here.
Right.
The values of A and the remainders.
Probably manually plug them back in, right? Like you could find those numbers and then just try which one fits into the 10 times 1 and which one fits into the 10 to the second power.
Yeah. And actually what the trick ends up being is that the last divisibility coefficient is always a 1 and the last remainder is always a 1. So you realize that those two are always the same, and then you start working backwards and you do exactly what you said, and you can actually use induction then to prove that it always lines up. And then so it was there were three main parts. There was the divisibility tricks, then it was the decimal patterns, and then the thing that ties them together is this idea of what I call the mapping problem, of trying to figure out how. And so that's the three parts of my research paper, and I'm just trying to get that proven, because this is just something that I wanted to do for me. I didn't really get a chance to write a thesis or anything in either my undergrad or my master's program, and I always wanted to do it. And so I went for it, and I think I came up with something pretty cool. And it's possible that some viewer is going to say, well, this is obvious, and that was, but this is all math that I came up with just from doing it on my own.
It's just a game. So everyone watching, it doesn't have to be practical. It can be just fun. You can just play with it. That's what the essence of math is, unlike what they teach you in school or when they try to make you like it by telling you it's practical. It doesn't have to be.
Yes. Doesn't have to be. No, but if you can understand all of this stuff, and again, so when I'm working with adults who are planning to take college algebra, the first thing I teach them is the divisibility tricks. Right. And then we talk about the fundamental theorem of arithmetic, which just says that all numbers can be broken down into prime parts. And if you can understand that, that's a good primer for a college algebra course. What's cool is that if you can understand all of this, that is a great primer for a number theory course, which, again, the divisibility tricks come in, but this talks about cryptography and computer science applications and all that stuff.
Cryptography is so much fun, and how modular. That uses so much of modular arithmetic and primes. I took a class in college. It was so fun.
Yeah. It's a good class. And this, again, what I proved here ties together section 5.1 and section 12.1 of this number theory book. And so it's connected to that. And if you can understand, and there's actually, again, I could talk about this for hours. There's a lot more that needs to be said here. For example, why is it for 7 that we get 6 digits? Why is it 6? And for 13, it's also 6. But for 11, there's 2 divisibility coefficients that come up. And for other numbers, it could be any number. And so it's well, why is that? And that actually is a concept that already exists. It's called the index of a number. And again, that comes up in studying cryptography and all these other things. Is it connects to some of these ideas. So if you really want a good intro to number theory, there's a lot more that we could talk about here that would sort of get you into that.
Wow. Have you ever thought about rewriting the book to include the connection?
I'm trying to write my paper in such a way that it bridges the gap between those two ideas. And I'm really hoping, now that I'm back in Michigan, I've actually been emailing with one of my professors at Oakland University where I went, and I'm hoping to actually meet up with him and go have a chat and show him what I've been working on. And I don't know, maybe some of the people in the math department would be interested in having me come by and do a presentation on me. But that's the whole point of the paper, is that it connects the
Right.
dots between. And when I started out, I didn't know that this book that I just happen to always have with me, like, I didn't know that any of this was in there. I didn't know that studying the divisibility tricks was going to connect me to why fractions convert to decimals and all this stuff. And again, we sort of did a very high level here. There's a lot of details that we could get into. One thing I want to circle back onto real quick, if we
At
can,
number one.
is that number one, should it be a basic number or should it be a coprime number? Because we said for the divisibility tricks, it's kind of boring, doesn't really matter. But let's take a second and think about, because we said for basic numbers, for these royal numbers, they should have a terminating decimal.
Right.
And for coprime numbers, they should have a repeating decimal. And so we're talking about the unit fraction 1 over whatever number we have in question. And the number in this case is 1. What is the fraction, what is the decimal for the fraction 1 over 1?
0 repeating.
1.0, which I would say terminates, because it's like, technically we don't even need to write the 0, but it doesn't repeat the same number on forever except for 0. But you could sort of say any terminating decimal, like 1/2. We can always say that it's 0.5, and then technically we can say you can always add another 0. But going back to what we talked about with the fractions out of 9, wherever those were, 1/9 was 0.1, 2/9 0.2, 3/9 0.3. Notice that this fraction 1 over 1 is equal to the fraction 9 over 9. And if we apply the trick for if it has a denominator of 9, what is its decimal? Well, we just take whatever the numerator is and repeat.
Wait a minute.
And I didn't learn this until I was in calculus 2, when you actually start doing infinite series. But it is mathematically true that the number 1 is equal to the decimal 0.9 repeating.
What?
And so technically, we could make the case that the number 1 falls into terminating because it's 1.0, but it is equal to the number 0.9 repeating. So it is also a fully repeating decimal.
How?
And most people, and actually I've seen people on social media get very upset by this fact. So I'm hoping that you know, if you want to just post this clip, people will get very mad and they'll want to watch the whole video. But people don't think that this is true, but you can prove that this is true. There's actually a very straightforward, using infinite series, again from Calc 2, if you want to challenge yourself, you can prove that this that basically this sum, 9/10 plus 9/100 plus 9/1000 plus just 9s all the way down, converges to 1. The limit is, so these numbers are equal. And so technically, again,
if the
1
limit is 1, does it ever reach 1? It just gets infinitely close to 1.
There's a whole bunch of technical points there about limits, but it's considered true that the number 0.9 repeating is equal to the number 1. These are the same value. And so it doesn't really answer the question of whether or not 1 is basic or coprime. It's kind of both. And I like what you said earlier about it being sort of in a superposition, where we can maybe, like, this is a weird terminating decimal, and then this is a very weird repeating decimal, and they actually ended up being the same number. And so it kind of breaks it in a very interesting way.
Wait, but you know about like the concept of physics, right? And light being both a wave and a particle at the same time. So like the wave is the terminating in a way. No, sorry, the particle is the terminating because it's like concrete, and the wave is not concrete. So it would be like the repeating. I wonder if there's any parallels there, because I find, because that's kind of like part of the basis of quantum mechanics. Something can be two things at once or have characteristics of two different things at once.
Sure.
Which is like the foundation of
that might be a point of further investigation, right? Is can we draw any more parallels between this and light or other sort of dual thing? Maybe some physicists could weigh in for us, because I really want to relearn physics. It's been a long time since I took physics, and the problem was when I took physics, I didn't know calculus because I was bad at math until I took differential equations. And then I
Yeah.
never went back and relearned the physics of it, and I just did full math.
Yeah,
So
physics with algebra is completely different than physics with calculus. When you have
yeah,
calculus, suddenly it's like, I don't have to have a sheet that gives me all the
yeah,
equations. I can memorize one and I can find the
just
others, you
derive
know?
them all exactly.
Yeah,
Yeah. Yeah,
yeah,
no, so I was bad at math until I became a math major. Like I had already taken all the calculus and all the physics, and like I didn't understand any of it. I just got through it. And then
yeah.
it wasn't
Most
until
of
I,
us do, most of
yeah,
us.
wasn't until I went back and relearned basic math that all of a sudden all the advanced stuff made sense.
Yeah,
Yeah.
yeah. I mean, we
But
need to start teaching math with, stories and questions, not
yeah.
not just
Well,
memorization.
and that's why, like, this is my little corner of how I teach math, is that I want to turn this into something that's a little bit more investigative. Like, it's not just that I want to tell you these things, I want to take you through the story. I want you to, and so this is what we focus on in the Wednesday night sessions that I do, is we explore this pattern from the basic of like starting with divisibility tricks and decimal patterns and work our way up and do all the different proofs and stuff. But I just think that math is supposed to be a little bit more fun and creative. It's supposed to be about making discoveries and figuring things out and asking why. And we don't ask why enough in schools, you know? Oh, Jen, I can't hear you anymore. I think I've lost you. I think it might be me. That's weird. Oh, maybe, hang on. Hello, can you hear me? It's probably because my phone is about to die. Um, well, what a crappy way to end it. After all that, no, I honestly, I think it's because. Here, let me do this real quick. Can you hear me now?
I think it was me because I was using. Can you hear me?
I can now, yeah.
I think it was me. I was using a microphone and I think one of them uncharged.
From now. We're frozen. Hello. Welcome back.
Can you hear me? And
I
can
can
you
hear
see me?
you.
I can hear
Yes.
you and I can see you. Okay, great. Well, I have a question though.
Please do.
Which is I think an optional challenge, but specifically for you.
Yeah.
Do you think that after you write the research paper, right, which is like formal, it has the formal language, it
Yeah.
has the formal proofs, if you can change that and write it as a story so that it's not just
Yeah.
for the academia?
Well, and that's why I'm trying to introduce this like analogy of like the royal numbers get the best
Right.
divisibility patterns and then the lesser ones and the so I'm trying to just make it fun and creative. And that's why I draw all these silly little pictures and stuff. Is like, I'm trying to express these ideas in a way that so here, this is that the proof that the fraction 1 or 9/9 is equal to the number one and how it all adds up and like all these
Wow.
different things. And yeah, I would love to turn it into maybe more of a story. And actually, I don't want to give too much away, but I am working on, or I say working on, I've got this idea in the back of my mind that's
Yeah.
come up recently about some characters that I want to write about.
Yes.
And what it is, and maybe it's not exactly this, but one of the characters like lives very ancient times, but he basically studies geometry and it sort of goes into some mystical. And so, like, I am trying to do some creative writing type stuff that ties into researching in mathematics in a way that's a little bit different. So I have some ideas there. It's just a matter of finding the
Yeah, I
time to
mean,
keep.
the reason why
Yeah.
I'm asking, so you know the book Alice in Wonderland, right? There's a
Yes.
version of it in which Alice is kind of in like quantum land. So it's
Yeah.
with physics, so it takes like a similar dreamlike approach where you can meet like different characters or particles or something, but it
Yeah.
explains like physics to you.
For sure. Well, and even the original Alice in Wonderland, Lewis Carroll
Guy
was
was a
actually he was
mathematician.
a mathematician, right? And so some people think that actually Alice in Wonderland is a critique of what was happening in the time in math research, where people were moving from like constructive proofs to non-constructive proofs, and he was trying to like make fun of the fact that nothing goes on. And so like, yeah, there's a ton of connections there. So somehow, and maybe you and I can keep thinking about this, is like, how would we turn this into a story of how numbers divide and all the different, pieces or whatever. But
Yeah,
I
that
just think,
sounds fun. I always think of each number as having like its own character sometimes.
yeah, for sure. And like, that's why, again, it's like nine is that like the right hand. It gets this very special
Yeah.
property because it's sort of like over all the other commoners because of its close connection to the base and like that kind of stuff. So maybe we start off with some, or maybe it's
Yeah,
like the,
yeah. I'll be honest, there was a time where I thought that my undergraduate thesis was going to be
yeah,
to rewrite that Alice in Quantumland book to be more modern because it was like it used older English and like some parts,
yeah,
had new discoveries for physics. I didn't end up doing that. I ended up doing my thesis on like the math of tango, but you
sure.
know,
Which your thesis paper is very cool. I love that you did that. That's such
it
an
was
awesome
fun.
thing.
It
Everyone should
was
check
fun.
that out. Yeah.
But yeah, we should think about that some more.
Yeah.
And if
Well,
anyone has
any
any ideas,
yes. And so for me, my next big step, actually, I don't know if you can see it up there. I was doing a webinar the other day, so I put some books up there. But that top book is the abstract algebra book that I learned from. And so abstract algebra is sort of the next type of math that I'm going to go back and relearn because I
mm,
think there's more that we can say on this problem. I think that this somehow relates to group theory and some other things. And so this is still a work in progress. There's still a lot more to be done. But
for abstract algebra, can I
yeah,
recommend a really good book?
please
So
do. Yeah.
when I was actually in abstract algebra, it didn't
Yeah.
really make sense to me. I was kind of like, I passed. It was one of
Yeah.
the hardest classes
It is. It
in the
really is. Yeah.
moment to understand. However, I found this book a couple months ago. It's called I think The Love of Math. I gotta find it. It's by Edward Frank, and it's called, where is this?
The love of.
Or the math of love, or the love of math. Some one of those two. There's the word math and there's the word love, and it's word love, and it's by Edward Frankel.
Edward
And
Frankel, Love and Math.
there we go, Love and Math. That book, I'm telling you, it's a great story. Number one, I haven't fully
Yeah.
finished it yet, but the way it introduces you to abstract algebra, once I read the beginning, it made my entire abstract algebra class make sense.
I love that.
Like we started with a point, he connects all of it back to symmetry, which makes
Yeah.
it so understandable, like all like groups and rings and everything, and it
Right.
was like, wow.
Yes. And I think, again, that's part of the problem is when you learn something like group theory, they're just throwing the theory at you because they know how to, here's the
Yeah,
starting point, here's what we're trying to get to, but
here's
you
a
don't get that,
definition.
right. You don't get
Yeah,
that sort of introductory,
where it came
exploratory.
from, what
Yeah.
is it even? When everything got abstract, like there was nothing to hold, I was like, I don't even understand why what we're working with.
Right,
Why we're doing.
exactly. Which made it a lot of fun, but does definitely make it a challenge. So that's sort of where I'm going next. So maybe sometime soon we can chat more about like group theory and that kind of stuff.
Yeah, there's an audio version of this book as well, which I
Oh,
think is super
cool.
helpful because I
Love
don't love
audiobooks.
sitting and reading all the time.
I'm right there with you, especially when you're like traveling and trying to do things. It's good to even just go for a
Yeah,
walk and listen to an audiobook. Yeah.
yeah, totally, exactly.
Yeah.
So
Cool. Well,
that's
again, Janet, thank you for the chance to like this has taken up a large part of my life the last year or so, and it's just cool to be able to share it with somebody because
I'm
you're really the
so
first person to
glad
ask
for
about
you
the
to
full
share it.
thing, you know?
I'm so
And
excited.
there's a lot more nuances and other examples and things we could have looked at. But if anyone has any questions or thoughts, I'm happy to connect with anyone and chat about this stuff because this is what I love to
Yeah,
do.
leave your questions,
Yeah.
comments in the comments,
Yep.
and maybe we'll have a book at some point.
Maybe we'll have
You do
something.
know I
Yeah.
publish books, right? So
Exactly right. Yep. You are my publisher
make
when the book gets done.
that happen.
Yeah, for sure.
Awesome. Anyway, well,
Cool.
thanks for joining, everyone. See y'all
Till
another
next
time.
time.